and welcome to today's Saratech enablement session. My name is Andrea Hall, and I will be your host today. I am the Customer Relationship Manager here at Saratech, so if you've called our support line, there's a good chance that we've spoken. Presenting today, we have Mark Anderson, who is an Applications Engineer here at Saratech, and he's going to be telling you about some awesome advancements and new things that we have here in NX-CAM. This is only part one. We will have a part two. He just had so much information, we weren't able to cram it all into one session, so we want to make sure that we spread that out. Our sessions do run about 30 minutes each, and they're all recorded and posted to our Saratech YouTube channel. So if you missed any of our past sessions or you want to check out some of our past sessions, you can check them out on our Saratech YouTube channel. We do meet here twice a month. We're here just to learn new tips and tricks, and then just talk about new and old features that can help you in your everyday tasks. Next slide. Yep, this is an open forum. So if you have any questions or comments during the session, just feel free to go ahead and type them over in that questions box over on the right-hand side. I'll be monitoring that, and then I can just interrupt Mark during the session and just let him know about your questions or comments while he's presenting. You're also welcome to save those till the end, or you can also type them into the little survey that pops up right after the session ends if you'd like to have one of us follow up with you. And with that, I am going to pass it back over to Mark.
Hello, my name is Mark Anderson. As Andrea said, I'm an applications engineer with Saratech, and I specialize in NX-CAM. And today we're going to be going over the new modifications and advancements in NX12, not just the CAM side, but also the interface and some of the other options. As Andrea said, this is a two-part series, so this is going to be the first of the two parts, and today we're going to be talking about the comprehensive solution for part manufacturing, which is the entirety of NX-CAM, and then we're going to touch up on additive manufacturing, machine line planner, and some of the newer features in NX12. So as you can see here, this slide, it represents the new modifications that are in and advancements that are in NX12 for manufacturing. So they've done a lot in the mold and die industry. So they've came out with a new option, a new operation, excuse me, it's called adaptive milling. And what adaptive milling does is it's NX-CAM's initial effort in the iMachining volume mill style of roughing strategies. What this does, instead of the traditional roughing strategies that they default to half diameter depth of cut, 3/4 of the radial engagement, and it's just slower RPMs, slower feed rates, hogging material out, and that's traditionally how it was done. Newer machines, newer materials that machines are made out of, they just don't have the rigidity that they once had with the big block style castings and foundations and stuff. They're making high-speed machines. And even the lesser quality of machine tools, and I don't want to say a name or anything, but we all know which machines are the sheet metal type of machines that you just can't really rough really hard with them, like say a 3-inch face mill, 200 thousandths deep. It just doesn't handle it very well. Stall the spindle out, doesn't have the horsepower. With the adaptive milling, instead of going that shallow depth of cut, large radial engagement, it takes an extremely large depth of engagement and a very shallow radial engagement. So you may have, if you say you have a 1/2-inch end mill, you're going to go 90% the flute. 90% of the flute that's available will at all times try to be engaged, but you're only going to go 20 to 30% radially engaged, but you're going to go 2 and 3 times your RPM and feed rates. So the volume of material removed when you do the study from traditional styles to current styles, the volume of material removed is greater with the adaptive milling strategies. And the adaptive milling that lends themselves very good to the sheet metal style machines, or the machines that have very little horsepower, and they're meant for lighter cuts, finishing style machines. Like one of the good machines to talk about, it's not a sheet metal machine, it's not a lesser quality machine, it's just a machine made for a very specific purpose, and those are the Fanuc robo drills. They don't have a very large amount of horsepower that they can yield, and they don't have the power to push them. They're meant for very light, shallow depths of cut, and the adaptive milling, it lends itself really well to that style of machine. You don't reach the the axis max for your servo motors or your pressures or your torques. So you don't risk injuring the machine or damaging the machine by trying to go too hard and heavy. We have advanced finishing strategies where we have adaptive engagements and exit strategies. They've done a lot for smoothing on the toolpath, not just for your exit moves or your entry moves, but smoothing in your strategy from moving from one motion to the next motion. We also have the production machining, where you can build the machine line planner, where in this module you can build your entire shop. And what it does is it does the spaghetti string study, which the spaghetti string, what you do is you take your part, and if you have your shop, you would go in and you would travel with that part all the way around your shop with that string to see how many times it crosses paths and how messy that path is from start to finish, so that you can then streamline your shop and the method of production from start to finish so that you can optimize that. You can also automate it with your NC programming, not to mention just your machine line planning to plan your parts progress through your machine tool, but you can also automate operations with the feature-based editor and the knowledge editor. When you go through the feature-based programming, out of the box you get a knowledge base that the machine tool, or I'm sorry, the machine operations and the tools are set. You can't change those. You can teach in operations, but you can't change the tooling or the conditions in which the tools are called or the operations are made. With the advancements in NX12, and I believe it started in NX10 and it slowly progressed to NX12, to where the feature-based editor, when you created these rules and these conditions, it had to be done in the knowledge-based editor, and that was a specific type of code. It wasn't C++ or Python. It was just conditioning code, if statements and then statements, type of macro B style programming type thing. Now inside of NX they have a dialog where you just go and teach, and inside of that dialog, inside of NX, you create the conditions, you create the operations, you create everything. So it's a very conversational style now. So people that want to really progress their knowledge base and use the feature-based programming for parts that are prismatic or 2.5D style parts, you can do that much easier now with NX12 than you could in previous versions. And they also did a lot of work in the mill turn programming. You can now seamlessly mill turn program from start to finish. You have multi-channel for upper lower turrets, doing multiple work on left and right spindles. Things of that nature now have gotten much easier in NX12. We also have the complete, I'm sorry, hold on one second. We have the complete part machining, and they've came out with a few new operations, complete new operations. And along with the adaptive milling, they have the turbo machinery, which is not a new option or new operation, but they've made the options inside of the operation much more fluid and easier to use. And they also have a tube machining. Tube machining is the picture in the complex part machining area. That's a radial or a axial compressor blade. The turbo machinery will do axial or radial blades. The tube machining, it's built more for ports on engine blocks or port style of objects. They've also done a great deal of enhancements with the robotic machining enhancements. Previously, you would write your program in 5-axis, and then at the end of it, you would introduce the robot, and then you would place the robot. You would articulate the joints of the robot to make sure that you aren't over traveling or getting extended. And once you enhanced it, then you would repost process it for the robot. Now it's programmed exactly the same as that, except they've made it more streamlined from start to finish. So it's much more friendly for us to program. We've also done a great deal in additive manufacturing. We have powder bed fusion and the HP multi-jet fusion support in NX. We have a great module for additive manufacturing in NX CAM. It does the multi-part nesting, so a 3D nesting algorithm is included in that. And we have a build strategy that's embedded inside of NX that will give you your cycle times and let you manipulate that build strategy. Our CMM inspection programming, they've done a lot with the CMM. One of the main things was previously it read external DEMIS programs, but the code had to be exactly right. Now it's formatted to read current and past DEMIS programs. You just import them in and you can test them out just like you can the G-code simulation. And also the circular point sets, the inspection points, you can keep the probe down inside of a cavity and do a circular inspection so that your motions are reduced. And then for tooling design, we have the automated feature recognition, which is in the feature-based manufacturing. And then we also have the accurate tool costing, which is the it's a costing module that helps you cost your tooling, your tools, your every piece of that to where it's a great quoting module. So going into this, the mold and die machining with NXCAM, with the adaptive roughing strategies and the different strategies that they've manipulated with your entries and exits and smoothing, we can machine high quality mold 60% faster, which is a big deal in the mold and die industry. So if you previously quoted out molds, you can accurately cost out those molds 60% faster now. The mold and die industry also, here's our highlight to our adaptive milling. It's a high-speed roughing strategy, deep cuts at high feed rates, smoothing, flowing toolpath so that you don't get into a compression area. If you're only engaged 20% of the tool or 30% of the tool, you don't ever want to get past that, because once you start getting past that, and if you ever get into a 90-degree engagement, that speeds and feeds will definitely be detrimental to the tool. So they've got the smoothing, flowing toolpaths, and they've made it to where the approaches and the toolpaths will never get into compression zones of that way. And it gives you a consistent tool load. One of the most important things when you're roughing very quickly and aggressively, or if you're running on hard materials, is the ability for it to be a consistent load. So if you've ever done just a cavity milling operation, when you get into different areas, you hear different tool loads. You can hear a chirp or you can hear a chatter area, and what that does is it's being inconsistent with that tool load. And when you're running, you can hear the differences in that tool load on the machine tool. When you run the adaptive roughing strategies, you can hear a constant, consistent, smooth load on the tool, which is very important when you're talking tool life. The benefits to the customer is reduce the machining time, like I said, up to 60%. It is ideal for hard metals. It works on everything that you would want to cut, and it's going to completely replace the cavity milling operation in the future. We will always have the cavity milling operation, but the adaptive roughing strategy, adaptive milling, is going to take over. If you're not using an adaptive style of roughing strategy, other companies will pass you by very quickly because of this 60% increase. If you're going to cost out or you're going to quote a job with traditional cutting styles, you're going to be higher than most companies that are using either our adaptive milling or the iMachining or Volumo plugins for NX. And as I said, for hard materials, the adaptive milling strategy works the best because for hard metal milling, you want that very long axial depth of cut, but very, very light radial depth of cut. And for hard metals and your end mills, they have very specific tolerances and speeds and feeds that they need to be ran at. And it's very easy to plug those speeds and feeds into the adaptive milling cycle. And it extends your tool life by up to 4%. And that's one thing that I always like to talk about when I'm talking about adaptive roughing is the extends life up to 4%, because I believe it's much higher than 4%. If you take into consideration the traditional method of using tooling, you're always burning up half the diameter of the tool or a little bit more than half the diameter of the tool in height at the end of the tool. So the top part of the tool is almost brand new. So what you have to do is you send that out to be reground, they cut that off, and we all know that reground end mills never function like they did when they were new. So that tool now is going to be used for roughing or for some other type of application. So 3/4 of that tool is still new, but can't be used to its efficiencies. With the adaptive milling strategy, you're using 90% of the flute. So you're going to use up the tool in its entirety. When you send that out, it's going to be radially reground. And then you've already got the cost of the tool, the life out of the tool. It's already paid for itself. So you could throw that tool away and not lose any money on that tool. But the traditional methods, you're always having to consider in how many times can it be re-ground, what can you do with it after it's re-ground, and how are you going to use that later. So with the adaptive roughing, you don't have to do that. So you get a much more cost-effective tooling cost. And I'll show you that in an operation here. So going into the adaptive demo. So here I just have a plate, and here I have an adaptive milling operation. And you see it's exactly the same as our cavity milling operation. The only thing that it does not have that cavity milling does have at this moment is a specified cut area. And the reason why they've done that is because they're building this operation from scratch, and it's much easier to build it, let industry use it as a volume to volume operation. So what it's going to do is it's going to take our raw stock, compare it to the finished part, and then it'll take that excess volume and it'll create a toolpath for that. In the future, Siemens is going to include the specified cut area, because if we have say we have a 4x8 sheet of 4140 that we're doing a progressive die shoe on, we don't want to just say blanket the entire part volume to volume. That would be an extremely long process for that tool to make all the different roughing strategies for all the different pieces of that die. So we would like to, like we do with cavity milling, we'd like to do the divide and conquer method. We'd like to start somewhere and then we'd like to finish somewhere, so we know where we are. That is coming. It's just not out in NX12 right yet, but it will be. So we have all the same settings, same tool axis. Some of the things that have changed though in our cutting parameters, we have our connections, optimizing, and cut directions. I always like to alternate the cut directions in roughing. So we have all the same information as we did in our cavity milling operation, so it'll be very familiar with you. Most of everything is exactly the same. We have our collision check here. So once that's checked, what it will do is it will, if it runs into an area where it collides with either a non-cutting portion of the tool, the shank, or the tool holder, it'll omit that piece of toolpath, and then it'll come up and it'll tell you. Now right here is where it's a little different. So we have our step over percent of tool flat. Our step over is 30% of the tool, but our depth of cut is a consistent 95% of the tool's flute. So what that does is it goes to our tool and it says how long is our flutes. Our flutes are 511 thousandths tall, so it's going to take 95% of that. So it always looks back at the tool. And then once you set this, you also have to set part and stock, and that's already been set, your part and your blank. And once you process it, you'll see it's a very quick process as well. It processes the toolpath very quickly. And this it's included in that 60% of in investment, or 60% faster speed of creating the cutting path and doing the manufacturing, the cutting itself. So you see, I'll show you what it's doing. So it's only taken that much because of the level, the flat that it was at. It's taken right there was a cut depth. So the next depths that are not on a flat will be in the adaptive roughing style. It still does as the cavity milling did. So there is a true adaptive milling roughing strategy. 95% of the the tool's flutes. And then another major benefit of this is with cavity milling, all we could do is we could select one cut method: cut part, follow part, follow perimeter. Now what adaptive roughing does is it'll start out as the one that you had selected, but then it will also morph. So when you go down here and you find you do not have a selection for that, and what it's going to do is it's going to choose all the different cut patterns that NX has to offer, and it'll pick the best one to use. So it'll do a morphing style, it'll do a spiraling out, a frame milling, and a D-slot tricordal. So, and that's where they get their advantages. So now moving back to the demo. So some of the mold and die machining enhancements with the finishing strategies are the new finishing capabilities. We have a much more consistent step over. And then our machining across gaps, previously, if the tool was able to fit into the gap, it would try to go in there. And we would have to do a multitude of things. We would either have to put a sheet over it, trim it, or create a stage model and use our synchronous technology to remove that to get a good flowing surface so that our tool cut the best that it could. With our machining across gaps, you can specify an amount, and if that gap is smaller than that or larger than that, it will, if it's smaller than what you have designated, it'll cut right over it. But it will match the surface that it was on and the surface it's going to with the same topology that it was cutting. So you won't get any deviation. If the gap is larger than what you specify, it'll try to go in. So they've made a bunch of different benefits to this finishing strategy by adding these couple of different additions here. The consistent step over machining across gaps. The benefits to this are you achieve a much superior surface finish, and it eliminates the prep work when they're prep work, that's talking about, as programmers, our prep work with creating stage models and removing that topology so that it cuts well. And it also reduces work from us as programmers to have to go in and create those models or to have to overprogram to miss those features. So we've expanded the smoothing options as well. We have the optimized toolpath, and it smooth engages into the material, which is really important when you're cutting harder materials or you're choosing to use a very aggressive roughing strategy. That entry can very well break your tool if it's done incorrectly. We have smoothing, retract, and transition moves, and then it eliminates sudden stops and change in direction, as I was talking about those compression moves. Those compression moves, if it goes into any corner and you designate 20% or 30% of radial engagement, the corner will force it to engage more, and then that's considered a compression zone, and it causes a lot of things to happen. So we want to stop that from happening. So what it's done is they've eliminated those sudden stops and those change in cutting directions, and it minimizes the tool wear, it reduces the machining time, and it improves the accuracy. So the two operations that I'm going to go on to next are, they consider built-in expertise. It's the tube machining and the turbo machinery. They have created an operation with very few selections will create that very, very precise, difficult 5-axis toolpath very, very easily. So here we're going to talk about our turbo milling and our tube milling, our turbo machinery and our tube milling operations. It's specialized operations for hollow, narrow regions for parts like is shown, but it was also mainly built for the automotive industry to cut manifolds, the ports and manifolds. And what they show you here is just a straight closed off 2D cross section and a guide curve. And this operation, it will also, in manifolds, what you see a lot of times is you see an air disbursement nodule, and it'll be in the inside of the port. And what it does is it disturbs the airflow from inlet to outlet so that it creates turbulence, so that the air is turbulent as it goes into the engine. And it will also produce a toolpath that will cut those nodules, and as many as they have in there, very easily. And it's built for spherical style tools, but it will also rough them out with ball end mills. It does not, or bowl end mills. It does not like square end mills, so it has to have a radius on the corner of the tool at minimal. So it's efficient roughing and finishing strategies for these tubes. Automated tool orientation, precise control of the cutting parameters. And then the benefits is a streamlined NC programming, one operation. It eliminates errors on the shop floor, it shortens the machining time, and it improves the surface quality. You can see here at the bottom picture, it's showing an axial fan blade. So this is an impeller blade, and it pushes air up and down, not radially in and out. So what this one is showing is the turbo machinery. And our turbo machinery, it's built and designed for this style or for the impeller, the radial impeller that I'm going to show the demo on. So here's the demo for these two operations. So here we
And
have the
just a quick
turbo.
reminder to, sorry, Mark, just a quick reminder to anyone that's on right now. If you have to hop off a little bit early, we are recording the session and we will send out the link to the session. Just wanted to let you know since we might go a little bit over time today, which is totally fine.
Okay, this one here, I'm showing the radio impeller, and the way that this operation works, it was a pretty ingenious operation that they built. You build a geometry node where it's called blade geometry. The part axis is the axis of rotation, which is your z-axis, straight up and down. Now you're going to specify your hub, which is the greenish area there. Then you specify the shroud, which the shroud is the orange area on the large blade. Then you specify the blade sides, and you have to do this in the right sequence. So you do the hub, then you do a blade, and then the splitter has to be the one to the right of it. So then you specify the blade radiuses, which is the green, and then you specify the splitters, which is the entire splitter. And then you tell it a number of rotational copies it's going to do. There are 6 copies of this particular blade and this splitter. So once we hit OK to that, we go in here and we have the actual operation. We're choosing that geometry so that we don't have to, you could set these in the operation if you want, but it's much easier just to create a geometry node, and then those will be already preset, just like your workpiece and your blank is. Your blade rough geometry, your drive method, here is just, they're very, very minimal inputs from the programmer, which is amazing for the type of operation that it creates. So once you fill these out, everything is exactly the same. Your cut levels, cutting parameters, and then when we generate this, so we have our multi-blade rough, our multi-blade, the instance, so I've copied that, and then our finish, splitter, hub, and blend. So it's going to go through these, it's going to produce those toolpaths, and it's going to show you the one toolpath that was created. And you see at the bottom it's processing. It's a little bit longer for this particular operation to process because it's going through and it's checking the shank of the tool, the cutting edge of the tool, the holder. Everything is being checked along with the cut to make sure that it's not hitting anything. And if it does hit something, then it goes through a process of alteration, and it moves the tool off of the collision until it's clear. And the parameters are inside the operation where it says tool holder allowance, tool shank, and non-cutting surface. They're defaulted to 100 thousandths, but you can change those. So the toolpath that this is going to give us is a default. I haven't changed any of the parameters to it. And as I said, what it's doing is it's going through and it's processing each of these individual toolpaths. But we've only programmed one blade and one splitter. And then what it will do is it will create that instance. And you see there it's finishing the blade. So then for time's sakes, I'll just go ahead and show the previous that I have here. So when I verify this toolpath, you can see the verification is just showing the tool, and now it'll show the stock as well. And for a 5-axis toolpath out of one operation, that's extremely powerful. And I have actually created many of these impellers, axials and radials, with this operation, and it is a very, very applicable operation. It's not just a pretty picture that they created that's not very applicable. It is very applicable, and so is the tube machining. These operations, they're very strong. So as you can see, it's going to cut out the blade and the impeller, and then what it will do is it'll come back through and it'll do a rotation and finish them. And then what it does with any copy, it's going to have an area of overlap. And then what it will do is it will copy that overlap, or it will merge that overlap to where there's no excess toolpaths. So that's the turbo machinery. Now the tube milling, here we have a tube. This is just an elbow connector. And then I have the tube, the roughing operation, and the finishing operation is exactly the same. We have our part. You don't have to have a blank because it's not looking at the blank. Here's our cut area. I selected, there's multiple depths areas in here, so I just selected these two surfaces, and then you have to select a central guide curve. That central guide curve here, and then the same parameters. You have tool axis. You can change it if you would like to, or you can leave it for default. I leave it for default so that the system picks the best orientation. And here are the different rough machining parameters, and it's also using the adaptive milling strategy, step overs here, and the direction of cut. So once you have these programmed, and I want to show you how fast this is. For this type of operation, this is very quick. You saw how fast or medium the turbo machinery was for all the toolpath that it created. It was actually very quick, but it created a lot of toolpath. This turbo tube milling cycle, it's not creating as much toolpath as that was, but it's extremely more difficult because it has to get inside of this ID without hitting anything, and it has to figure out how deep can I go? Do I switch to this side? And you have different abilities. You can go as far as you can from one side. You can go one side then the other side. You can do other side only. There's many different options available to you. So it's on 79 of 100. So we'll let that process out. And if you had to create this yourself before this operation, it would be every bit of 10 operations to get it roughed out, the different tool orientations, then the 5-axis tool paths. You'd probably have 4 or 5 5-axis operations to be able to get that with the surface finish that this would create. And to do that, I would say 10 operations easy. And now we can do 2. We can do a tube rough and a tube finish. So this is going to be 79 of 100 now. So, and once this finishes, and I'll let this play, you'll see how accurate this toolpath has to be. So now you see the toolpath that was created, and it is going from both sides. I'll go ahead and verify this so you can see. It says a blank is needed for orientation. We'll just say it has 10 thousandths all the way around it. And you see I have a spherical tool. It's going to come in the bottom, and it's going to do circular adaptive roughing strategies until it gets through. Then it'll go as deep as it can, and then it'll come back the other side. So it's preparing this part, adding that stock to it, and then we'll be able to show what it's doing. So you see there, it's cutting, and I'll show it as it would be in the machine. So you can see this is a full 5-axis toolpath that's going to go through and cut. It's going to follow this drive curve, and it's just going to spiral itself down. It's not going to come back out like the adaptive roughing strategy. And then it will go as deep as possible. Then it will come in this side here to finish. The only thing that I have found that you have to worry about when you use this operation is that when you do go from both sides, most of the tubes that you machine, you have to go from both sides unless they're very small. When you do choose to go from both sides, when this side here goes and it has material to cut, there's tool pressure. And once it falls off that material and it does the overlap pass, a lot of times it likes to overcut in that overlap pass only because of tool pressure. If there's material there, it will be the same pressure this side as this side. But when it falls off of that material, it wants to leave a ring or two. So you just want to be careful about making sure that overlap is exactly the same and not to let it overcut too much. So you see it's doing as much as it can now. It's switched over to that side and it will finish it. So that was the tube milling and the turbo machinery options. And those operations are going to make, if you do 5-axis programming on that style of pieces, it's going to make your life a lot easier. So here's our complex part machining for the robots. They've expanded those applications for the robots for part manufacturing. The program robots for machine tending using NXCAM, that would be adding loading parts, things like that. We have a very accurate simulation using the VNCK kernel. That is the cinemeric controller. It gives you numeric control interface to run the post-process code through as if you were doing it on the physical machine tool. And then we have new post-processors for the new machines, the Yazka machines. Customer benefits: program complete manufacturing cells using one system, accurately simulate the numeric equipped robots, and you can create controller-specific output, like using variables or doing macro programming style type things. And we've just seen a difference in the building of these robots. Previously, they were used mainly for positioning and loading, unloading, and they were pretty inaccurate. And now they've gotten to be robust and very, very accurate. So you can use them for all the different pieces of manufacturing. And then your production machining, you can automate the entire process with the plant line module and then the knowledge base editor. And then here's your production machine line planner. You distribute and you balance your machining operations over multiple steps. It has an integrated NX CAM for NC programming, bidirectional change management between programming and line planning. And the benefits of that are reduced investment in machinery, reduced planning time, and increased throughput. So this is a beneficial module that if you have a large shop, if you get into the machining line planner, at the end you'll see the benefit by controlling the manipulation from start to finish through your shop. And then the seamless mill turn programming, they've enhanced the visualization using the in-process workpiece. You can seamlessly transfer the in-process workpiece between the milling and the turning operations. Previously, that wasn't the easiest thing to navigate. You can keep track of the in-process state of the work, identify potential collisions between the workpiece and tool holder. That includes multi-spindle machines moving from one spindle to the next. The benefits are the faster programming of complex processes, error-free machining, and optimized operations. So 3 takeaways from today's sessions are the adaptive roughing operation, tube machining operation, and the turbo machining operation. I would really, really recommend that you guys use the adaptive roughing operation. And if you do tube or turbo style manufacturing, those operations will become invaluable to you. The next session is the part 2 of what's new in NX CAM, and it's happening Thursday, April 18th, 2019, and I will also be the presenter for that. So if you're ready to take it to the next level, Saratech, we offer engineering services to address your demand for advanced engineering capabilities. We offer additive manufacturing capabilities, Markforged, HP, Big Rep, and Union Tech. Thank you for attending. Here are a few links that you can follow that will give you more information. Here's a couple.
Thank you, Mark. Great job. Oh, yep, sorry, go ahead.
That's okay. Here's just a few from NX or from Siemens. They just have a lot of good stuff in them as well, and they will be in the video, so you can copy them from there.
Yep, perfect. And then in part 2, correct me if I'm wrong, but you're going to be going over the new turbo milling operation, and then the new guide curve operation, and then the current state of and the future of NX CAM and what's coming up.
Correct. Yep. I did the turbo machinery on this one, but I will be going over the other new ones during part 2. Okay. And we'll be talking about where NX is and where it will be in the near future.
Okay, perfect. Well, thank you everyone so much for joining. And if you did register for this session, we're going to go ahead and just pre-register you for part 2. If you cannot make it to that session, we will send out the link. So by registering, all that means is that you're welcome to join us on the live session, or you will you will get the link in your email. So I don't think we got any questions today during the session, but if you have any questions that you want us to follow up with, please just go ahead and put them in the quick little survey that's going to pop up as soon as we end this session right now. So thanks again, everyone, for your time, and we will see you in just a couple of weeks for part 2. Great job, Mark.
Okay, thank you, Andrea.
Bye.
Bye.